simulated individually, running in a given physical configuration that at the same time is a plastic configuration. So the shape of the respiratory tract is flexible, and the trajectories of the particles can be followed individually. What they can use this for, the example in the figure, is how this can be personalized to some extent, trying to understand how different configurations of the respiratory tract will influence in the way the drugs that are fabricated in the form of aerosols are flying over the respiratory tract, understanding where they are hitting and what can be the best way, what can be the best design in terms of the size of the particles. This is another simulation, just to give one other example. Same thing, trying to simulate at the level of an organ the movement. In this case, is movement plus some of the electrostatic properties. One of the things that they can use this type of systems for is to map back real experimental data, trying to understand how the data fit with the different movements and the different conditions on this particular simulation. So it's a way of coupling data with simulations at the level of organs. Obviously, there is much more to do. This is only two examples, 2 organs. There are many other systems that will have to be simulated at this level. So it's interesting. It's a very consuming task because, like in the case of the particles, to be able to get data in a realistic way from that, you need to simulate many times, many millions of particles, and this is done with fluid dynamics equations that are pretty expensive to calculate. And there are many questions then, when you do these simulations, there are many questions that we can ask, questions that are related with the overall performance of the simulations, how to find the key points, how to find specific events on the simulations, and also how to organize the computers to perform the simulations in the most efficient way along the trajectories. So this is nice, and it's a full activity in this area. Still, there are many things that has to be solved before we can really profit in biomedicine, in biology, from this type of simulations. First of all, as you may realize, these simulations are not related with the cellular level. They are done at a very macroscopic level, but it's impossible, how things are done now, to understand the relation between what is happening in the simulation and anything that is happening at the molecular or the cellular level. They are right now completely disconnected. Second, it's very difficult to personalize. It's very nice to have this general model, but it's very difficult to say this is the model for this particular person in this particular condition. So this going from the general to the particular is also going to be a very much needed effort, and it's something that is not there right now. And it's difficult to find applications. The simulation is nice, you see things happening, but how are you going to use this information? Is the simulation telling you more than the experimental data that you use to build the simulation? And we already discussed this topic yesterday. The perfect simulation will be the one that is providing the data that you already have experimentally. So it's still I would say, a very much on the debate topic, how we can, what is the right level in which this simulation will tell us things that we don't know. Obviously, the other way to go about that, the other way we are exploring, like many other groups, is going, instead of bottom-up to the big systems, going top-down, start from the molecular level. What we would like to do is to simulate, for example, in this case, tumor with all the complicated microenvironment, the different cell lines in the tumor, the immune infiltration, all the conditions of oxygen, possible drugs, and everything. As you know, to do that, we are using a combination of molecular models, models of pathways, or metabolic models, most likely represented as Boolean models to make things feasible. And at the same time, we are using cellular automata, agents, to represent cells. So in the pictures, each one of the dots, each one of the small balls, will be a cell that is informed with a particular model of the cellular state represented by a Boolean model. The simulation is not running, doesn't matter. So in our case, we are using this combination in collaboration with groups in Curie and Indiana University and Norway, models of the molecular level, models of the cellular level, trying to reproduce the conditions of tumors and making simulations that will reproduce things like, trying to understand things like what is the response to drugs. So all this is ongoing activity. Obviously, there are many difficulties at this point. Difficulties that have to do with lack of data. When we want to reproduce the molecular level, we know that we don't have all the information about pathways or metabolic conditions. We don't have all the parameters to do these simulations, so we have to jump over the things that we don't know, and we need more data to fulfill many of the conditions and the parameters on the equations. At the cellular level, we have done progress trying to understand how is the response of individual cells to treatments, for example, to drugs, but still, in most of the cases, the simulations are still not very, at least it's very difficult to move simulations to be able to reproduce conditions like drug treatment or like synergies between drugs, or even to reproduce the different behavior of different cell types to a given drug. If we want to move from the cellular level to the multicellular level, all these difficulties will be even more complicated once that we want to understand how the cells are interacting and how they are interacting with the environment, whatever this is, the extracellular matrix or the conditions on a tumor. In most of the cases, I highlighted in the slide the lack of data. We are facing a problem that, as you know very well, is fascinating but extremely complex, a problem that is far more complex than the problems that physicists have been facing in their simulations. And for such a complex problem, we need data, and I guess this is what we are here to be able to generate enough data to try to solve some of these problems at the molecular, cellular, or multicellular level. Even if we can solve the problems at these different levels, we will still have a problem of integrating the information from the molecular to the cellular to the multicellular level. This is called the multi-scale problem. There are many different groups working on that. There are very good work done by centers of excellence, the BioExcel Center of Excellence. There are all the development that were done by the different national projects. I highlighted here the German virtual liver project, or all the ongoing activities of the virtual physiological human. So it's not that there is not activity in these areas, it's only that the problems and the challenges are very big, and we have to really do a lot of more work on the simulation side, on the data gathering side, to make progress. And I would say the only thing that I can say is that the only solution to these problems is to go and do it. We need to get more data, to do more simulations, to generate more results, and to go back to more simulations. And there is no magic solution to any of these problems except working on them. So this is from a failed competing proposal that was called Digital Twin. The proposal failed, as a pity, for a number of reasons. But still, the paradigm of that, I think, is an interesting thought. So digital twins, as you may know, is the term that is used in the industry for the systems that are producing simulations that are running in parallel with the real system and trying to foresee what is going to happen with the real system in a way that there can be measurements on things done to prevent a number of events. I give you the typical case, will be a car factory. It's a big complex thing producing cars. There's a digital twin system running in parallel that will run in as much as possible a similar system to the real car production system in a way that they can predict what is going to happen. Are we going to run out of some of the components? What's happening if we stop it here? What's happening if we change from producing one thing to producing another thing tomorrow at 9 in the morning? So these are the typical use of the digital twin system. The idea here was a digital twin for medicine. Can we do the same thing in medicine? Can we have, in the example was Anna, going to the clinic, getting some measurements done. In this context will be single-cell measurements done, but you can imagine that in a real medical scenario there will be many other things, many other type of data that will be required. Can all this be then shift to the digital world, to the digital Anna, where there will be a model of Anna that will be fed with the data, produce some experiments, some possible treatments for this condition of Anna, and the information will be sent back to Anna. Obviously, it will be easier to do experiments in the digital, with the digital Anna, with the digital twin of Anna, and at the same time, many of the conditions could have been pre-calculated for many of the events. And then the information will be back to the real world, and the clinicians and Anna will take a decision about what to do. Obviously, this is a scenario that is not possible right now. I just showed you what is the level of simulation that we can do of some organs, so there is no digital twin that we can implement right now. The question for me is this something that will be possible in the future? And when is the future? The future is in 50 years, in 20 years. How much can we do to speed up the process? Because the truth of all that is that we need systems to help clinicians to take decisions. And these systems are going to be, sooner or later, around this paradigm, sending information to a digital system that will give us possibilities, possible scenarios of treatment, possible solutions to a given problem. So these are, for me, interesting questions in this setup, in thinking in 10 years from now, how much of this can be implemented in the real world? For what systems, in what specific cases, with what limitations? Obviously, high-performance computers can be used for simulations, show you some of the possibilities. They can also be used for other things, and in this context, it's particularly interesting, from my point of view, to explore the possibilities of understanding networks. Many of the problems in biology can be phrased in this language of biological networks. In our case, we are interested in problems related with genomics, splicing, and chimeric constructions, chimeric proteins and chimeric RNAs. The problems of relation between diseases. We were talking yesterday about disease focus. More and more, we think in diseases not as a single type of disease, but diseases given by conditions or subdivisions of diseases in a smaller subgroup of cases. But at the same time, in real life, diseases are not happening in isolation. Diseases are happening, unfortunately, to people in combinations, comorbidities, the presence of different diseases in the same person. So understanding the relation between diseases becomes not only a very important medical topic, but at the same time, a very interesting tool to understand the biology behind the diseases by understanding the combinations of diseases. And obviously, we are also interested in other types of networks, in these cases, networks that are related with epigenetic information, representing chromatin capture experiments in the form of networks as an alternative way of analyzing the information. And there are many other ways in which we can represent, there are many other areas of biology that can be represented as networks. Networks can be very interesting, but can get really very complicated. I give you a very simple example of how easily and how quickly complexity grows in any biological problem. We were wondering about this a very simple problem, how to find the relations between two ontologies. This is the gene ontology, that describes biochemical information, essentially. And the other one is HPO. This is an ontology that describes symptoms. The two ontologies are related by genes. There are some genes that are annotated in the two ontologies. So in principle, we can imagine ways of connecting the information from one to the other. This is a rather simple thing. We can say something like, I have this type of symptoms. I don't know to what biochemistry they can correspond, so I can go to another term, I can go to a gene, I can go to a gene ontology term, and find a relation. So I can do this type of exploration, connecting information from two different ontologies. So in principle, this is a very simple operation. I have two ontologies, they are not that big, and I want to be able to connect them. Once that you try to do this systematically, the thing gets complicated. The number of possible connections for these two ontologies is around 600 million connections if we are only exploring 4 jumps from 2 in one ontology connected with a gene. If we want to do a larger exploration of 6 or 7 possible pathways, the number will grow exponentially, so we can be really very big explorations. To do that, to be able to explore this network, to be able to travel between these two simple ontologies, we end up in a very deep problem of exploring very large networks. And then you end up, again, in the need of methods to do that. In this case, it's a collaboration with people working in my institute in massive parallelizations in a way that we can really explore all the possibilities in a computer for these 600 million combinations. So network biology is a good way of exploring biology, but as soon as you enter in any of these problems of networks, you end up facing very complex algorithmic problems, and many of them are highly demanding of computational power. So all this is about things that we can do with the data, but then to be able to do things with the data, we need the data. So in the next part, I will tell you a little bit about how we deal with biomedical data in the context of bioinformatics, and some of the European infrastructures dealing with biological data. And some of the ideas, and then I will tell you something about some of the ideas of what we think can be avenues for new developments in the future. We are not the only ones producing data. As you know, physics is producing data in quantities that are similar to what we produce in biology or even more. I give you 2 examples. This is Gaia. This is a project from the European Space Agency. This is the map of the galaxy, trying to map all the stars and all the planets or things that we can find in the galaxy, or the distance with the other galaxy. The numbers they are talking about is, depending on the level of distance and resolution, well, a few hundred or thousands of millions of events, of stars, or objects, if you want. This is a very large project with a very, all the countries involved, very big networks, all the observatories, all the different type of instruments sending information, and then it's a database collection problem. The database is at the Barcelona Supercomputing Center. We have the same problems that we have with the data. The curation of the data, not losing the data, getting data from large providers and small providers, the quality of the data, being able to compute on the data to do all this, to find the elements, to find the distance, to find the properties of the different elements. So it's, with enough organization, this can be done, and this project has been running for a number of years very successfully. So in a sense, it's good to think that we are not alone dealing with this type of large-scale and data problems, and this has already been solved in other areas. This is from the large-scale project on particle physics. There's people around the CERN, the Super Collider. Same thing. There's a paper a few weeks ago, beginning of the year. Open is not enough. It's not enough with having all these data from the Super Collider. They need to be able to compute on the data and to compute on the different phases of the data and to be able to recover all the data that they have done in the different experiments. So again, large-scale consortiums, very well funded, very well organized, handling very large scale, very large data set of, in this case, probably of 10 times larger of what we have right now in biology. So the alternative and you have here all that in biology is around fair principles, making the data findable, accessible, interoperable, and reusable. As you know, this is absolutely popular with agencies. There is no local agency, there is no international agency that is not talking about making the data public. And no, I cannot say there is nothing wrong with that. We obviously want to have the data open and accessible and being able to use it. I mentioned two different efforts, European efforts, which you have already heard about. One is the European Open Science Cloud. It's still a little bit unclear what is going to happen and how this is going to develop, but certainly there's a political effort in putting together the different organizations in Europe to be able to provide data in an accessible way. The other one that was already mentioned yesterday, and I think is particularly interesting for us, is the initiative for medicaments in Europe. This is the largest public-private partnership in the world. Pharmaceutical companies, now there will be other companies too, and the European Commission putting huge amount of money into different type of consortiums, generating data or analyzing data. Now, in the transition between the second phase of IMI and the possible new project that will have a different name, one of the key considerations is, along these years, what has IMI produced in terms of data, where is this data, how this data can be analyzed, how the data can be put in value for the companies and for the public. And I think we are in a very good position to influence how the next phase of IMI is going to develop, because this is really moving huge amount of money and is also directly connected with the interests of industry. I will be careful about all that. And yes, it's important to have all this data accessible. This is not the only mission we have. It's not only making the data accessible, it's being able to generate the data and being able to analyze the data. So if I want to put this in a moderate way, I would be very careful about what is the effort that we have to dedicate as a consortium to do science and to keep the data. If we only put effort in keeping the data and annotating data, we will not progressing in science. If we only do experiments and analysis and we don't put any effort in keeping the data in a proper way, we will not contribute to the overall progress. And the balance, I think, is very important. Obviously, Europe is getting organized to do these things. Elixir was already mentioned. This is the European Bioinformatics Infrastructure. I'm sure you have heard about that. This is organized in nodes in different countries. Every country is organized also as a network inside the country. A number of these developments are very important for what we are doing here. The European Genome Phenome Archive, the database that is storing the information of human genomes. The Beacon project, ways of analyzing or asking for what information do you have in a repository without breaking the laws of confidentiality, being able to understand where is information about a given mutation or a given phenotype. All the efforts of Elixir in providing a single identifier for all the resources in Europe in a way that you can explore information in different repositories without having to have a new certification, a new identification. All this effort of Elixir. Elixir is now a partner of the Global Alliance for Genomic Health, and all these three projects, the Genome, the EGA database, the Beacon project, and the Elixir identification system are at the same time projects of the Global Alliance. So all this is working not only at the European level, but at the international level. I just wanted to mention one of the efforts in the context of Elixir, because I think this also can be very relevant in the context of the talks of these 2 days. One of the things that we are more interested in the context of Elixir are automatic systems for benchmarking bioinformatics methods. So we are interested not only in providing methods for analyzing this. In this case, in this example, for example, text mining method will be the next example. Not only being able to provide the methods, but also to provide, together with the methods, the systems to evaluate them in scientific and technical terms, and being able to do this live in a way that, as a biologist, you will go to a web page and say, these are the methods for analyzing multiple sequence alignments, and according to the last benchmark, this is the one that is working better for these conditions. And to be able to keep, so these are the technical developments, not going to enter into the details, obviously, but these are the technical evaluations, and these are scientific evaluations. In this case, the method is for methods doing finding orthologs, but this is just one example. So this will tell you if the systems are up and running, how much time do they take, and this will tell you what is the best performing one according to a given data set. And we have put an effort to do this for many communities, trying to make a system that is a stable and general benchmarking system. This has been in many different domains. I'm not going to say much about that. This is text mining. There is a big effort at the scientific level and at the technical level to provide systems able to understand or to interpret or to extract information from text. This is particularly relevant in biology because the difficulties in extracting information from medical records and from medical information. There are developments related with information extraction at many different levels, and there are infrastructures. OpenMinted is an European infrastructure, in a sense equivalent to what is Elixir in the domain of bioinformatics, dedicated to provide methods and systems for extracting information in biology, in biological terms, or biomedical terms. It's important here the problem of the languages. Now, if we do this extraction of information in medicine, we will do this in the medical records, and the medical records are written in the specific language in the different countries, so the extraction problem becomes a problem of extracting information in a multilingual setting. Two ideas here. So there are many developments on the computational side, thinking on how we are going to be able to access the information, the medical information that is distributed in the different hospitals and the different repositories, and how we are going to connect this with the different methodologies. The two ideas we are discussing these days are these two ones, the patient dossier and the continuous computing. Just to say this in a few words, the patient dossier is the idea that instead of asking the systems to do a lot of work at the level of the data, we want to put more the burden of the problem in the question, in a way that when a physician or a biologist is asking a given biological question, he or she will not have to worry about where is the data and what are the methods. The question itself will be written and formulated in a way that will be able to find where is the information, what is the right information to use to answer this question, how to access the information, what are the conditions for accessing this information, and what are the method repositories and the specific methods needed to answer the question. So in a sense, we want to put the effort in the formulation of the question at the computational level in a way that the user will not have to worry about all these details. And something similar is for the continuum computing. The idea is that the user will not have to think about, for this data, I need to use this computer because it's accessible or easy or the adequate one. The system itself will be able to take the given question and find what is the right environment for a given question, trying to do the computation in a faster, more efficient way possibly close to the data itself. So these are concepts. The question is how to go from these conceptual frameworks to actual implementations, and this is what we and many others are putting effort in doing. One thing is obviously is to have this data in the different repositories, in the different databases, being able to find the information, being able to handle the information. The second question is what is called the data integration problem. The ways in which this can be described, or the way I want to explain this here today, is using multi-layers. That is one of the possible approaches to this problem, combining information at different levels. The examples, the easy examples are these type of things. These are 4 scientists going to 3 conferences, so you can now map how these 4 scientists are interacting. They are interacting because they told to each other or because they went to a talk that was given by the others in the 3 different workshops, and then there will be different relations, and then you can start integrating the information, trying to find what is the the relation between them and at what level they are transferring ideas from one to the others. The thing can get more complicated. This is another approach based on networks. This is for someone traveling in a city, how to connect the information from 3 different transport systems, the tram, the metro, and the bus. These are the metro, bus, and lines, and then you can start mapping how different people use the different transport systems and how the systems themselves are linked. So we maintain information in different layers. The layers are connected because the metro station will be close to a tram station, and then you can start tracing how different people move to understand what are the main use of these transportation lines. In the case of biology, we can use these multi-layers to find trajectories, how genes are connected, for example, or communities, how different genes or proteins are performing common functions. There are many things that we can put in these multi-layers. These are examples, physical interactions, drugs, mutations and variations, pathways, or reactions with metabolites. As soon as we start putting this information, the number of trajectories connecting all this information in this estimation for this particular data set, where the estimation is around 100 million trajectories. So handling this information, 100 million trajectories becomes a problem, an interesting computational problem. Can this be useful? Show you examples without entering into the details. We are using this to understand the relation between severe and less severe cases of a given rare disease. If you do this by simple integration information, you don't understand the relation between the genomics of these two type of cases for this disease. If you use typical functional enrichment analysis, you start seeing things, but you cannot really understand very well the differences between the different type of the diseases. When you use multi-layer analysis, then you can really go deeper and understand the relations between these two types of diseases. And again, when we use this information, we obviously face problems. This is an example mixing information from electronic health records, transcriptomics, symptoms, and microbiome. And then the thing becomes really a new and complex problem because we don't have the same individuals in all the layers. We don't have a person for which we have all this information. We have information from a group of patients at the level of medical records, another group at the level of transcriptomics, another group at the level of symptoms, and another group at the level of the microbiome. And now these relations are not one-to-one. It's a complex setup, and there are solutions to be explored to solve these problems. So data integration is a complex problem. Having the data accessible is not enough. How to interpret the data becomes really a complex problem by itself. I showed you one type of development. We are interested in this multi-layer. There are many other possible ways of analyzing information, but this is, I would say, a particularly promising one. And all these computational methods are really very demanding of computing time. To finish, I have a couple of slides on artificial intelligence and machine learning. This has been already discussed yesterday, so there is no need to go in any detail, and I'm running late. We have a lot of hopes, and these are some just two recent papers, Atul Butel and Eric Topol, on the promises of machine learning in particular, in providing systems that will help doctors in the process of taking decisions. The truth is that this system are already in use in many areas of engineering, but we have more problems in biology, or there are less of these systems accessible in biology. Still, things are working. This is an example from Andrew and Jay, assigning cases of arrhythmias. And machine learning systems are better than the doctors in classifying cases of arrhythmia, what is not surprising because it's just a very accessible computational problem that does not solve the problem of the treatment of arrhythmia, only solve the initial problem of the classifications. There are many applications. This is a particularly interesting one. I'm not going to enter into that. You probably have seen the papers solving or making a big progress in predicting protein structures. A very open and complex problem. Now, Google DeepMind has made a lot of progress on that. So there is actual progress that can be done with machine learning techniques in very hardcore molecular biology problems. this is, in a sense, even if machine learning is not new, what is new is there's the new type of deep learning techniques. It's probably very much of a new development. And everything has to be taken with care because the applications are very powerful, but at the same time, the publicity around these things is not always very positive, and we are in the point of producing a counter-reaction. These are what are called adversarial networks, systems that are able to confuse the classification systems, and these are all the possible ways in which a hospital system can be attacked by these adversarial networks that will confuse the classification system of the hospital, will, in a sense, hack the hospital systems. And this is the reaction of the Spanish newspaper wondering about that. So artificial intelligence has a lot of promises, but for different reasons, the public perception may not be as positive as we think it is, and this is certainly dangerous. Sorry, I'm running late. I'm finished with that. So I showed you a number of possibilities for the use of high-performance computing. These are new machines. These are new machines for machine learning. This is getting very big. The largest computer in the world is a computer designed, or with a design that is very appropriate for doing machine learning. Just to give you an example, Europe is running late, but still putting money, hundreds of millions of euros, in buying new computers, and this will be probably very adequate for making machine learning, for making machine learning applications. So artificial intelligence is not a single thing. Deep neural networks are not new, but they are not magical, but they are very powerful. We need still to understand better how they are working, and there are many other alternatives that can be implemented in biology. So I finished with that. As I say, I just went through all the possibilities, summarizing many of the things that were said yesterday in terms of the data, the importance of keeping the data, annotating the data properly, that we are making real efforts and progress in being able to put the data together and doing data analysis. And this data analysis in form of networks or the computational systems has to be put along and together with the simulations if we want to make progress in providing biomedicine with systems that can help in the decision progress, integrating molecular information with other type of information. Thank you very much. And we are late.
Yes, but it would be really good if we can have a discussion around all the topic of interest for lifetime. So, questions?
Hi, Alfonso. So you covered a lot of ground. Difficult for me to follow everything. But what I was really interested in, and I'm not sure if you talked about it, but let's say, even if you did, could you clarify or tell us about your thoughts about how people active in lifetime would connect to what you do, or how you would connect to them, or if you think there's an interest in this really?
Well, I hope I say something about that. So from my point of view, we are in a very critical moment in which a number of fields that were completely disconnected until now, high-performance computing, that is a big investment in Europe, it's a big investment worldwide, it's a big investment in Europe, the biomedical infrastructures, Elixir and the like, trying to organize and maintain the data, the initiative like IMI connecting with the pharmaceutical industry that is in a critical point, trying to decide what they are going to do in the future. These are like three main big investments at the technical, scientific, and economical level that are right now disconnected but getting increasingly interested in understanding each other. What they are missing, from my point of view, is a vision of how this is going to be progressing in the future in a way that real progress can be produced by understanding the underlying processes behind diseases. So there is the interest of high-performance computing, the interest of the biomedical infrastructures, the interest of the industry around IMI in understanding the causes of diseases. And to be able to do that, they need the initial molecular data. They have the tools on the high-performance systems, they have the tools and the systems to keep the data, they have the tools and the systems to do drugs and drugs developments. They need to have the models of how the molecular processes are working. And this is the connection. This is the right time to put all these efforts together under the light of how we get the molecular data that they need to make progress and being able to build on these infrastructures.
Thank you. So Fabian, please.
Thanks for a nice presentation. It's really interesting how you describe sort of this HPC angle, and particularly in physics, also in some physical simulations, you show very nicely that there's for sure a need for these high-performance computation-based simulations. I guess 10 years ago, so when we started with systems biology, right, we also had this overly promise that we can build up bottom-up models. But I think for some reason we weren't able to integrate the data so well. So you're saying we should take that up again, or should we more focus on the machine learning techniques which are not doing so much of this molecular thing? So you're basically your first part of the talk, which was more network, bottom-up, and then this data science-based things. Do you see these things, these connections now happening in applications that you're studying?
I think that, like many things, and what you describe you describe this in a very good way. Like many things in science, they go in ups and downs, times of up and times of down, no? And we have seen this in, machine learning is a good example, the natural language processing is another good example. I think that we are now in a critical point in which we can again try to build bottom-up systems because we understand better the data, and we have data in a way, and this is what you are representing here, in an unprecedented way. This was not possible to do it 10 years ago because we didn't have the data and the data integration. Data and data integration and machine learning, for me, are fusing in a single thing because we need the data integration, the machine learning to understand the data. If we only do that and we don't put this in a simulation framework in which we can foresee what is going to happen, do predictions and go back, it will be very difficult to interpret the data. So I don't see, at least in my mind, there is not a conceptual difference between all these approaches. They have to be part of the same thing. Yeah. And we are in a position now which we can use the computer system that we were not able to use before. We have the data we didn't have before, and we have new techniques that we didn't have before. So I think it's a time for a new app on this type of approaches.
So this is a fantastic pitch for Work Package 3-4 intro, I would say. Thank you so much.
So it would be great if some of the medics in this audience could perhaps raise their voice and comment, because I feel that it's really important for all the different type of people to really see where the challenges are, and with the spirit that we are trying to develop with Lifetime, get a good communication throughout all the aspects that we do encompass. And so I would like one of you in the audience to sort of say, how do you see, from the perspective of a doctor, the interest of linking up with these approaches and the way dealing with your patient can be improved? Okay, good.
Yes, my name is Thomas Gasser. I'm a clinical neurologist, the Hertie Institute for Clinical Brain Research in Tübingen in Germany. And this is actually a topic that is discussed on many levels. For example, there is a German initiative, a medical informatics initiative that tries to make clinical data that are acquired in routine clinical practice available to research and to build models and so on and so on. And it turns out a little bit like Fabian Theiss says, we start with big hopes, and it turns out that when we crash on the hard floor of reality, that there are many obstacles. Data protection is one, but only one. Very heterogeneous procedures in clinical settings is another one. Data compatibility between one hospital and the other, between even one department in a hospital and the next department, is usually not there. So I think it's extremely important. And looking at this program here of the meeting, I already noted that there was very little representation of, that there was a lot of focus on diseases, and that the target of the program is to give better cures and better diagnosis to diseases, but there was very little representation of the medical world, the actual clinical world. Here, having heard yesterday's talk, I think it was very justified because you focused very much on the methods, and the clinicians could have only told you we're not there to provide the data, but I think that it's very important to keep that in mind for the future trajectory of the program.
So it's good that you're mentioning this, because there will be, for sure, in the next part of the session, a lot of discussion where the medical aspect should really engage strongly. But I really wanted to sort of already make sure that people raise their voice. So any other comments in that direction? I think this is the forum for discussion. So please go up.
I think that one could already go very far with setting up a couple of cohorts or linking up on clinical cohorts. I'm myself a researcher in the Alzheimer field, and so in UK they have several large cohorts where they follow people over time to see how they evolve. And so there are usually already measurements in place to keep the data and to give open access. And also I'm thinking about Biobank, where you have then this type of information. And so one of the things I would like to see to happen in this consortium is that we have that type of cohort for different diseases, and link that to the data, and link that to genetic data, and then link that to a method to get access to fibroblasts or blood cells from these patients, which allows us then to make iPSC cells which cover the genetic risk, and which can then use for polygenic risk scores calculations, which we can then link back to the clinical information which you get from these cohorts. And these cells can then be used for basic research, where you can go in any direction, chimera, etc. And so I think this is feasible if you do it, if you don't want to encompass everything, but if you say, look, we select 10 cohorts or 10 consortiums of cohorts, and we define upfront the access and the confidentiality and the ethics around it. And I think that would be an enormous weapon in our enterprise.